Before we get into this, two questions that you will not be asked on the quiz tomorrow. Number 127, that was the question about aluminum dissolving into water and making a complex ion, one of those water molecules releasing a hydrogen. Number 127, don't do that one. And then, if you did any of the multiple choice questions, chapter 13, number 12. Chapter 13, number 12 is a bad question. Please write down that those are not to be. 127. Is that 127? Yeah, it's 127. And then chapter 13, number 12. That's what I'm talking about. Yep. I thought it said 127. Okay, if I said number 27, scratch that. Sorry. Is 127 is no good. No, and then chapter 13, number 12. Review question. Those are the only two. Yeah, that was 127.
And then he said, no, he's 27, then I'm telling you.
We're good now. Okay. So, in this chapter, all we've seen so far is acids that have one hydrogen that come off. And how do we deal with those? How do you find the pH? Somebody last hour said, I was doing the problems over the weekend. I felt like it was deja vu. I kept doing the same thing over and over. Yes. A lot of repetition in this chapter. All the techniques that we learned in this chapter, we're going to apply in the next chapter, plus more. Next chapter is, it's a big one. Buffers. It's the reactions between acids and weak bases, or bases and weak acids. Reactions involved. So there's lots there. So the last thing in this chapter, the root here is prot. It's dealing with protons. We normally don't get into subatomic structure, how many protons or neutrons or whatever, but often a hydrogen ion is referred to as a proton because that's all that a hydrogen ion is. Hydrogen is a proton with an electron around it, and since you have a hydrogen that has lost its electron, all that's left over is a proton. So when we talk about polyprotic acid, it just means polyprotons or polyhydrogen ions. In the book, in the appendix, there is the Ka table on page A22. There's the Kb table on page A23. And then right in between those two, up above the Kb table, there is a Ka of polyprotic acids table. We'll need to look at that when we do those kinds of problems. There's not many polyprotic problems that are assigned. I think there's two. So it's real quick. I'm going to use phosphoric acid as the example that I give today because phosphoric acid has 3 hydrogens. When we do the more complex thing with 3 hydrogens, it should make the things that have 2 hydrogens simpler. And that's what my thought is today. So let's take a look. What I want you to see about polyprotic acids is the assumption that we make that every molecule is going to release its hydrogen ion before any other second hydrogens come off. So the first K is, I shouldn't say that, that's not true. The first hydrogen is going to get released and that is going to come to equilibrium first. Then the second step is going to start. So the K value for the first hydrogen coming off is pretty high. I mean, phosphoric acid is a pretty strong acid. It's weak, but as weak acids go, it's fairly strong. 0.075 would be the Ka value for that. And you know, as the Ka table goes, it's pretty high up there. I want you to notice though, that's only for the first hydrogen coming off. This ion dihydrogen phosphate still has hydrogens that can come off of it. So once this thing comes to equilibrium, then this one goes to work and it starts to release hydrogen. And notice the K value for this one losing hydrogen. It goes way down. It's about 100,000 times smaller than the first K value. This step comes to equilibrium, and then the HPO4 ion releases its hydrogen. And notice the K on this one. It goes down about another 100,000 times. So what ion are you going to have very little concentration of when H3PO4 is in water? Just the PO4 with all the hydrogen stripped off of it, you're going to have a really small concentration. In fact, that's the last example we'll do to see if we can figure out what the concentration of PO4 is. See how the first K is way bigger than the other two? Way bigger. When we want to know what the pH of a polyprotic acid is, these second two steps are not going to contribute hardly any hydrogen ions compared to the first step. So that gives us this statement in red. When you're dealing with polyprotic acids, if the question asks you what's the pH, just do the first step. You don't have to do any more than that. Find the pH from the first step. Now, what I'd like to do in the next slide, I only have 3 slides today, that was the first one. The next slide, we're going to confirm that this is true. What I'd like to do is not do all 3, but just do the first 2 steps to show, after the first step, what is the hydrogen concentration, and then what is the hydrogen concentration after the second step. And I think it'll be very clear that we don't need that second step to find the pH. Okay. So this is what we're going to do. We have a 5 molar phosphoric acid solution. I want to come up with what the pH is. Which means we'll need the hydrogen concentration. So we'll make an ice table out of the first hydrogen. That's just step 1. In fact, I'm going to give us lots of room to do that on. Ice tables should be very comfortable for us by this time. I'm just going to skip right down to this step. This is going to go to X and that's X. So that Ka1, polyprotic, we're going to number our Kas, equals, and I don't remember what it is, 3 point something, oh no, 7.5 times 10 to the negative 3. And that's equal to x squared over 5 minus x. This K is pretty big, but we're going to use the 5% rule anyway. Neglect that minus x term, and we're just going to take the K times 5 and take the square root of it. Solving for x gives us the hydrogen concentration. Now I want you to notice, not only does it give us the hydrogen concentration, of course it gives us the H2PO4 ion. I'm going to write that in there. Normally I don't, but I have a reason for doing it this time. I believe we get 0.19 for this, if you calculated it. 0.1 time, well, 19 molarity. Take that, and let's do the next step. The next step is going to take H2PO4. Now we have a concentration of it. That concentration of H2PO4 will start to release its hydrogen. And it's a much smaller concentration than when we started, isn't it? All right? I'm doing this on purpose. I just want you to see the chemical equation. H2PO4 is releasing a hydrogen ion, then it goes down by 1H. So our initial concentration of H2PO4 is 0.19. So far this chapter, we've kind of become very familiar with the two products that are made starting at 0. Both products don't start at 0 for this one though, so be real careful and think about this. The hydrogen ion concentration is not 0 when the second reaction starts. We've produced some hydrogen ions. They're still there. So where the concentration of H2PO4 was 0.19, the hydrogen concentration initially is also 0.19. This thing is not dissociating into like just water. It's dissociating into now an acid solution. So our initial concentration of hydrogen cannot be neglected. It's also 0.19. And by the way, that hydrogen concentration is going to cause this thing not to shift as much to the right. That does affect it. We're going to see that in the next chapter too. All right, so anyway, can we be sure that this reaction will shift to the right? We're starting with some reacted there, some of one of the products. Will it shift to the right? Yes, it will. Why? Why does it shift to the right? I've said it a whole bunch of times in this chapter and last chapter. Because you can't, what? Come on, don't look at me like I'm a pink elephant. What can we not have at equilibrium?
Zero.
Anything with 0 concentration. Yeah. Can you breathe or something so I know that you're okay? All right, good, thank you. Thank you. That was kind of scary. You're never like this. Are you okay? I'm concerned about you. I know too much YouTube this weekend. I'm doing this for Grace. Is it Grace that's the catalyst for everybody? Grace, come back. We need you. So I'm going to make sure she watches this too. All right, so anyway, it has to shift to the right. You can't end with 0 of anything. The K value for this is small, but it's not 0, so it has to make some of the HPO4. Okay, so we know it's going to go to the right. This is going to go down by X, that goes up, and that goes up by X. So that at equilibrium it's 0.19 minus X, X, and 0.19 plus X. Now running through the K, this one is 6.2. No, not that way. 6.2 times 10 to the negative. So the Ka2 is 6.2 times 10 to the negative 8, which is, now it's not just x squared like we're used to. It's the two products multiplied together. X times 0.19 plus x over 0.19 minus x. Now the 5% rule says that if K is really small, which it is, then we can just neglect the change in a small x value. It's going to go to the right just a tiny little amount and then stop. So it doesn't change this 0.19, and it shouldn't change that 0.19 either, because it's really small. So that makes our math really kind of a joke in this case. Excuse me. This plus x term is 0, and that minus